So once again, welcome to my YouTube channel. In the previous video, we understood the instantaneous center method. Now in this video, we will understand the relative velocity method along with two examples. So I am sure that after seeing this video, there is no doubt in relative velocity method. Please see this video till end to understand the concept completely. It is also requested to like, subscribe and share this video. So in this figure, a rigid link is shown to you. This is a rigid link. And three different points we have taken on the rigid link. One is A, second is B, and third is C. So we know that this is a rigid link, and this rigid link is rotates about this point A with an another speed of omega into the clockwise direction. So the absolute velocity of this point A will be in any direction. Similarly, the absolute velocity of this point B will be in any direction. But when we are talking about the relative velocity of this B point with respect to point A, so it is always perpendicular to the line joining from point B to A. So this is point B, this is point A. We join the line and we are drawing a perpendicular line that represents the velocity of B with respect to point A. The sense of this velocity vector will be in such a way that it rotates this B point about this point A into the clockwise direction because the link is rotated into the clockwise direction. If we have some other point C, so the position of the C point we know because we know the distances AC and BC. So we can locate this point C. If we are interested to find the velocity of this C point also, so we join this C point with A point. We draw a perpendicular vector, okay, to this CA line, and the sense of this velocity vector, this is called VCA. The sense of this velocity vector is in this direction because and it's try to rotate this point C with respect to point A into the clockwise direction. So this is called the space diagram. And the second diagram is shown as the velocity diagram or the velocity polygon. So here first of all we mark the point A because about that point we want to find out the velocity of the other point. So A point we have marked with a small alphabet. Now to locate this point B, we should know the velocity VBA. VBA value we know because this velocity vector we know we have read the formula V is equal to R into omega. So VBA is nothing but the distance BA into omega. So this way we know the value of VBA. So with this V, this distance from A to B we know. But direction, to locate the direction of this AB vector is either parallel to BA or it is perpendicular to the line joining from B to A. So this is BA line. So perpendicular to this line or parallel to this VBA vector, we draw a line from this point A and we have marked this point B because this AB distance we know. To locate this C point on the link, we know that the C point divide the AB line in certain ratio. So in the same ratio, the C point divide this velocity diagram. So this way we have located this C point basically. And we have measured this AC. So this will give the velocity of this C point with respect to point A. In the space diagram, all the alphabets are capital, but in the velocity diagram, all the alphabets are small. So if we want to have a formula to find the velocity of any of the link point on the link, so we have VCA divided by VBA, that should be equal to omega AC divided by omega AB. Omega is same here because all the point rotates with the same rotational speed. So we have the AC divided by AB. AC we know, then AB we know, because all the distances means the location of the C point we know. So all the distances we know. We know the value of VBA because VBA is nothing but R into omega means BA into omega. So from here we have find the value of VCA. Okay? Or from this velocity diagram we can also measure this AC and this give the velocity of this C point with respect to point A. Again we have considered a rigid link. This is a rigid link and we have considered four different points on the rigid link: point A, point B, point C and point D. Point C is on the line joining B to A and point D is outside the BA line. And the location of all the points are given to us. This D point is at a location of theta angle from AB into the clockwise direction, and from if we see from B point, it is having an angle phi in the anti-clockwise direction. This way we can locate this D point, or if we know the distances AD and BD, so this way we can locate this D point basically. So this VA is the absolute velocity of this A point in this direction. So VA we know in magnitude and direction, This is the VB. This is the absolute velocity of point B, and we know this value in direction but not in magnitude. But we know the relative velocity of this B point with respect to point A. It is always perpendicular to the line joining B to A. So we join this line and we draw a perpendicular vector. So this gives the value of VBA to us, means the velocity of B with respect to point A. In this case, the link rotates into the anti-clockwise direction, so the sense of this velocity vector will be in this way. So this is the space diagram when we are drawing the velocity diagram. So first of all, we mark a pole point. Suppose O is the pole point here. A general point we can take here. So to represent the velocity of this A point, absolute velocity from this O point, because we know it magnitude and direction both. So with this O point, we draw a vector VA and we locate the point A. Once we locate the point A, then we have to locate the point B basically. So direction of this velocity VB we know. Okay. So from here, from this O point, we draw a vector which is parallel to VB vector. So this is that line. So we extend this line. We do not know where this line is intersecting with other lines. So we extend this line on the upper side basically. Then from this A point also to locate the point B, this relative velocity direction we know, that is perpendicular to BA. So we draw from this A point, we draw a line perpendicular to BA. So, and we can extend this line. So these two lines are meeting at this point. So this way we have locate point B. If we join with O to B, so this gives the absolute velocity of VB in magnitude. If we measure this line B to A, this gives the value of VB to us, means velocity of B with respect to point A. We have some other points C on the link, so we know its position, means we know the value of AC and BC. So this way we locate this C point, because as this C point divide this AB line, so in the same ratio this BA vector, velocity vector, is divided basically. So this way we locate this C point, we join this C point with O point. So we have the absolute velocity of this C point. If we join this C point with A, so we have VCA. Okay. If we join this C with B, so we have VCB. So this way we have find out the velocity of this C point with respect to some other point. To locate this point D, as we say that this D point is making an angle theta into the clockwise direction with AB line. So this is the AB line. So from this A point we have marked or we have draw a line at an angle of theta into the clockwise direction. So this is that line, and from this B point, if we see to locate this D point, we draw a line and making an angle phi into the anti-clockwise direction. So from here B point in the anti-clockwise direction, we draw a line where these two lines are meeting. We are getting the D point there. If we join this D with A, so we are having the velocity of D point with respect to point A. If we are joining out this B to D, direction is from B to D, so we are having the velocity of D point with respect to point B. If we join this D point with pole point O, so we are getting the absolute velocity. So this gives the value of VD. VDO or VD is same, because this is the pole point in this situation. So this we will see that how from the space diagram, how we are drawing the velocity diagram, and how we are finding out the absolute velocity and relative velocity of any of the point with respect to the other point. Here the concept of rubbing velocity is discussed. So here we have two links, one is OA and other is OB. And if we see that these two links are rotating into the opposite direction, this OA is rotating into the clockwise direction, while this OB is rotated into the anti-clockwise direction with a speed of omega 2. So at point B we have the pin connection, and here we have a pin whose radius is equal to r. So at this pin we have the rubbing velocity. So if we are finding out the rubbing velocity at point A, so we have to find out the relative rotational speed of both the links with respect to the pin. So here, when if the links rotate into the same direction, then the relative velocity is omega 1 minus omega 2, or the difference between omega 1 and omega 2. Okay, so this multiplied by radius, so this gives the rubbing velocity at point O or at pin O, if the links rotate into the same direction. If the links are rotating into the opposite direction, so the relative velocity is nothing but the summation of these two, omega 1 plus omega 2. So and multiply by radius of the pin basically. So this way we are getting the rubbing velocity at pin O. If the links are having the same direction of rotation, if they have the direction opposite to each other. Here we have discussed one numerical problem. It is a 4-bar chain A, B, C and D. All the distances of the different links are marked. They are in mm. So AD length is 150 mm, AB length is 40 mm, BC length is 150 mm and CD length is 80 mm. So in this case, this AB link is making an angle 60° with AD link, and the rotational speed is given of this link AB, that is omega BS would be equal to 12.56 radian per second, and this is into the clockwise direction. So we know this omega, we know the BLN, so we have find this value of VB. That VB should be equal to R into omega, means BA into omega. So BA is 40 and omega is 12.56. So we got this value of VB, and direction is perpendicular to point joining B to A. So we join this BA point and we draw a perpendicular vector. The direction of this vector is in such a way that it tries to rotate this B point about this point A into the clockwise direction, because this BA link is rotated into the clockwise direction. So here we see that A and D point are the fixed points. So we can mark these 2 points A and D as a pole point in this case here. And as we discussed that in the velocity polygon, we use small alphabet. So A and D, A comma D, A we have marked as a pole point in this case here. So first of all, this VB value we know. So we draw this vector. So from this A point, we draw a vector VB and we locate this B point. So this way we reach to the point B, and this VB vector we know in magnitude, because already we have find this value, that is a B into omega. Now after reaching to this B point, we have to locate to this C point. So we know that the velocity of this C point with respect to point B is perpendicular to the BC link. Already we have discussed. So from this B point, we draw a line which is perpendicular to BC. So suppose this is that line. We extend this line. We do not know where it is intersecting with other lines. Similarly, we know that the velocity of this C point with respect to point D is perpendicular to the link CD. So we draw one line which is perpendicular to CD. So from this D point, we draw a line, this line which is perpendicular to CD. So wherever these two lines are meeting, there we are getting point C. So this way we locate the point C into the velocity diagram. Now if we join this C with D, so we are having the velocity of C with respect to point D. Direction is from D to C. If the direction of the velocity vector is from B to C, so we are having VCB. So this is a graphical method. So first of all, we have to draw this space diagram, okay, because all the dimensions are given to us. And from this space diagram, we have to draw this velocity diagram basically, because we have the drawing instruments. We can draw the line perpendicular to any line, okay, on this space diagram and parallel to that line. So this is a graphical method, and we assume certain scale also to draw these two diagrams basically. Now after that, we measure this value. We have to find out the value of omega CD, with the rotational speed of this link CD. So to locate this omega CD, so this omega CD is nothing but we know that V is equal to R into omega. So this is VCD divided by CD. CD is the length of the link CD and VCD is the velocity of C point with respect to point D. So this is point C and this is point B and this is point D here. So this VCD, so this VCD, this is VCD, the velocity of C with respect to point D. So we measure this, and as per the scale we can convert to the velocity. So this velocity is coming out to be 0.385 meter per second. The CD length is 80, that is 0.08 meter. So when we solve this, we are getting 4.8 radian per second. So this is the numerical value. And now we have to find out the direction also. Yeah, so very carefully understand how to find direction of this omega CD. So here we have find out the velocity of C with respect to point D. So this is in this direction. Okay, this arrow is marked here from D to C. So this is D point, this is C point. So the velocity of this C point with respect to this point is in this direction. Means in this direction basically. Okay, this direction is shown here. This direction, the sense of this direction we can take from the velocity diagram. So this is in this direction. So if the velocity vector of the C point is in this direction, okay, so the C point about this D point try to rotate into the clockwise direction basically. So this way the value is 4.8 radian per second and the direction is clockwise with respect to point A. So this way we find out the direction of any of the uh, point on the link or the rotational the direction of the rotational speed of any of the link, okay, on in a problem. This is the second example of single slider. This is the single slider crankshaft, and here OB is the crank and BC is the BP is the connecting dot, and P is a slider basically. Okay, there are 2 points E and G. The location of these points are given to us. This BO is having a length of 0.5 meter and at an angle of 45 degree from inner dead center, and this is outer dead center. And this BO link is rotated into the clockwise direction. Okay. So this is moving from IDC to ODC basically. So the data given as the rotational speed of BO link is given to us, that is 18.85 radian per second, and we have to find out the velocity of the piston. This is the piston here, or this is the point P. So this velocity we have to find out. Then omega PB, this PB is the connecting rod in this case. So omega PB we have to find out along with direction. Then VE, we have one other point E on this link here. So velocity of this E point we have to find out. We have seen that there are different pins at point O, point B and point P because all are the pin joint here. So we have to find out the rubbing velocity at the pin of crankshaft O, crank B and then cross at P, and where diameters are given as 50 mm, 60 mm and 30 mm. So this is the actual problem. So first of all we understood how to draw the velocity polygon and then see that how to find out the velocities and rotational speed and their direction. So here first of all we have to draw the space diagram. So this is the space diagram, all the dimensions are given to us, and then with this space diagram we have to draw the velocity diagram. So we assume some scale and then we draw this diagram on the copy, and after that we assume some scale for the velocity polygon and then we can write here. So as we saw, this O point is fixed point here, and about that point this crank is rotating, so we mark this O point as a ball point in this case here. The velocity of this B point with respect to point O or VBO, or we call them as VB, is known to us, that is R into omega, means BO into omega. BO is 0.05 here and omega is given in the problem here, so we can find out this value of velocity of VB with respect to point O, and that is perpendicular to line joining BO. So from this O point, and if we see the sense, because this OB is rotating into the clockwise direction, so this velocity vector means the VBO will try to rotate this link into the clockwise direction. So this velocity vector will be in this direction here. So from this O point, we mark this point B, or this distance we know, and we mark them as a VBO, velocity of point B with respect to point O. Now we try to look at this P point here. So this velocity of this P point with respect to point B is perpendicular to the point joining P and B, or link PB. So from this B point we draw a line which is perpendicular to BP, and this is that line. We do not know where this is intersecting with other vectors. So we also know that this slider is always rotating along PO, because this is a slider basically, it cannot rotate, it is only can slide along this line PO. So from this O point we draw a vector which is parallel to PO. So we draw a parallel line, and where these two lines are meeting, intersecting, there we are getting point P. So we join this P point with O and we join this B point with P, so we are getting the relative velocity. So when we join P with O, we are getting VP. When we join B point with P point, we are getting the velocity of B with respect to point P. One more thing I want to explain here. If we are finding out the velocity of point B with respect to point P, so we draw a vector joining from P to B, and this is that vector. So this vector representing the VBP. If we are finding out the velocity of this P point with respect to point B, so we draw a vector starting from point B up to point P, means from B to P, that is into the downward direction. So they have the same magnitude but they have the different directions. So after that we have to look at this point E and G. So this E and G point are on the PB link. So we know the location of this E point, we know the location of this G point. So as this E and G point divide this line PB into the space diagram in the same ratio, this E and G point will divide this PB vector. So here this way we can locate this E point and we can locate this G point. We join E with O, we join G with O, we are getting the velocity Vg and we are getting the velocity V. So this way, with the help of the velocity polygon, we see that how we are finding out the relative velocity and how we are finding out the absolute velocity. Now after drawing this velocity polygon, we have to find the first the piston speed Vp. So we measure this Vp and that is coming out to be 8.15 meter per second, and this is from point O to P, means this is into this direction basically. After that, we have to find out the value of the omega Pv. So omega Pv is nothing but the rotation speed of the Pv link. So this is nothing but Vpb divided by length of the Pb link. So Vpb means the velocity of P with respect to B we have to find out. So velocity of this P point with respect to point B we have to find out. This is from B to P, means into the downward direction. So means with respect to this point B, if we see the velocity of this, so this is into the downward direction. Means about this point B, this point B point, this point P is rotating into the anti-clockwise direction because this vector is from B to P. Okay, so about this point, this P is into the downward direction here in this direction. And when it is the velocity is in direction, means this rotates this P point into the anti-clockwise direction. So this velocity we have measured and divide this PV length, that is 2 meters. So we got the value of 3.418 per second, that is into the anti-clockwise direction. This VE, this distance we measure, so we got the value of V, that is coming out to be 8.5 meter per second. So this way we got the value of Vp, omega Pb and then Ve. Now we have to find out the rubbing velocity at the different pins. So first the rubbing velocity at pin of crankshaft O. This is the crankshaft here, and here we see that this OP is a fixed kind of link which do not have any relative velocity, and only the one relative velocity is there, that is called the BO, because that BO is having some rotational speed. So at the pin at point O having only one velocity, one omega, that is omega BO into the radius of the pin at O, that is DO by 2. This omega BO is 18.85 into this DOE by 2 is 0.05 into, that comes to 0.47 meter per second. Now the relative velocity at pin of crankshaft. So at the crankshaft B, we have the pin. So we have to find the the rubbing velocity at that point. So we have to find out the direction of. There are two links associated with this B point, that is BU and BP. So with respect to that point, we have to find out the omega of this PB link and then omega of this BO link. Now let us see how to find out this omega PB. Already we have find out this omega PB into the anticlockwise, that is 3.4. So omega PB we can put here 3.4 and that is into the anticlockwise direction. This way we can mark it here. Now we have to find the this omega OB, means with respect to point B, what is the velocity of or omega of this point O or BO basically. So this is point B, this is point O. So the velocity of this B point, O point with respect to point B is along the B to O basically, means in this direction basically. So means about that point, this O point is having velocity into the down direction. So when this point is having velocity into that direction, means about that P point, this point O try to rotate into the clockwise direction basically. So this omega OB is into the clockwise direction. Yeah. So this omega OB value is 18.84. So we put this value, and these two links BO and BP about that point B is having the different rotational speed into the different directions basically. So we have to find out the relative velocity. So this is the addition of these two values. So here we can add these two values, 18.85 plus 3.4 into the radius of the pin at B, that is dB by 2, that is 0.06 by 2. So we are getting a rubbing velocity at crankshaft pin at B is 0.67 meter per second basically. Now we have to find out there is one more pin P here. So we have to find the rubbing velocity here. Again we see that there is only one link PB which is having a rotational speed. This BO is having a fixed kind of link, or we have a slider. Slider do not have any rotational speed. It is only having the linear speed basically. So only one rotational speed is there basically. So this omega BP we have to find out. Means omega BP. So omega PB is into the anticlockwise direction. So if we are finding out the value of omega BP, that is into the clockwise direction basically. So this omega BP is into the clockwise direction. So that is 3.4. Already we have find this value into dP by 2, that is 0.03 by 2, that is coming out to be 0.04 meter per second. So this way we can find out the rubbing velocity of the crankshaft at point P basically. Thanks for watching this video on relative velocity method. Here we discuss the complete methodology along with two examples. And I think with the examples, the concept is clear to you how to draw the velocity polygon and how to draw the space polygon and how to find out the absolute velocity, relative velocity and rotation speed of the links. So please like, subscribe and share this video.